Hi guys, so let's go over this one. I think it's the first one, so I don't think it's hard, but let's do it. So you have an electric field. Okay, so you have an electric field. So let's say the electric field is going this way, and you see here, this is the magnitude. So it's constant. So it's a uniform electric field. So the lines are equally spaced. And then you have a dipole, and the dipole makes a 30 degrees angle with the electric field. So dipole is a vector, so I'm going to make a vector here, right, which is P, and that angle here is 30 degrees. And the dipole, by definition, goes from minus to plus in physics. Okay, so you have a negative charge and a positive charge, and then the distance between them is given. So the distance between the two charges is 0.04 meters, and the charge are given in magnitude. It's going to be 2 times 10 to the negative 9 coulombs. And that's going to be the distance here. You have the distance here, which is d. So it's quite easy. So first we're going to find the physical quantity dipole. So that will be the dipole moment. By definition, in magnitude, is going to be QD. So only the magnitude here. So QD, so you multiply Q by D. Okay, and you should find 8 times 10 to the negative 11 units is coulomb meters. And I remind you that you can look at your equation sheet here. It says dipole moment. And here you have the torque. And you have the magnitude of the torque. It's a cross product. Okay, so then you can find the torque. The torque is, by definition, the cross product. So P cross E. Okay, so the magnitude is going to be the magnitude of P, the magnitude of E, and the sign between them. So here it could be tricky. Make sure that you attach the two vectors, so the vector E and the vector P, by their tail to find the angle. So that's the only tricky thing here. And you can find the answer. And then you see that you can be asked which way it's gonna spin, rotate. So the positive charge in that case wants to go with the field here. So that will be the electric force on it. And the negative charge here wants to go against. So that will be the electric force. Negative always wants to go against. So you take your thumb here and your hand. Okay. So it means it's going to rotate clockwise. And if you take your right hand and if you make it rotate clockwise, the thumb goes into the screen. So that means the vector torque will be into the screen. Okay, so easy. That was number 1. Okay, so let's do number 2. Number 2 is easy. You need to find the electric field at a given position, but it's 1D. So this is the x-axis, and you have 0 here. Let's say 1, 2, 3. You have 0.3. 4, 5, 6. You have 0.6. 7, 8, 9, and you have 0.9. Okay, so at 0, you have a positive charge, so 2 microcoulomb. at 0.3, you have minus 1 microcoulomb. So it's a negative charge. And then at 0.6 here, so 3, 4, 5, 6, you have another charge, positive, microcoulomb, 6, 7, 8, 9. So here you're going to place 1 coulomb of charge because you want to find the electric field here at this location. So I'm going to call that number 1, number 2, and number 3. So the electric field is going to be, we use the superposition principle, so you need to add all those electric fields. So from E1, you see it's going to be pushed away by this charge here. So E1 will be in this direction. And then E2, it's going to be positive, negative, is going to attract. Okay, so that's E1, that's E2. And then this one is going to push away. So that's going to be E3. And this one is supposed to be a little bit larger than that one. So E1, E2, E3. Okay, so when you add them up, you're going to get something here, right? E net. Okay, so by definition, the magnitude of E, like any electric field, okay, it's going to be K, and the charge, the source, times 1 coulomb over the distance square. So that's in magnitude. So because it's a vector sum, I'm going to say that the net electric field, so we always have K, so I can factor out. Okay, so it's going to be E1 because of this one. So it's going to be 2 times 10 to the negative 6, the distance square, so 0.9 square. And it's going to be, yes, in this direction. And then you have from this source here, so it's negative. So the electric field converge toward it. So it's going to be minus 10 to the negative 6, 0.6 square. And then you have from that source here, which is diverge, creating that electric field. So it's plus 3 times 10 to the negative 6. And here you have a 0.3 square. So you see, you can do, you can factor out if you want the 10 to the negative 6. And it's going to be positive, and you're going to find the answer. So you can factor out, right? You can have fun, 10 to the 9, 10 to the negative 6 if you want. So here you have 2 over 0.9 square, minus 1 over 0.6 square, plus 3 over 0.3 square. That's going to be 10 to the third, and you find the answer. Okay, so number 3. So again, this is not it's not very hard. So first, always you have to draw the situation, okay? And you have a charge, let's say, you have a charge Q1 at 0.3, so 0, 1, 2, 3 here. Okay, and this is positive. So positive 6 nanocoulomb, so 10 to the negative 9. And then number 2 is at 0, 0.1. So it's going to be here. And this one is negative. So negative 1 nanocoulomb. So it's a negative charge. You can even use color. So, you know, this one is positive, this one is negative, and number 3 is positive here, and it's going to be 5 nanocoulomb. So I'm going to call that number 1. I'm going to call that, or they call that Q1, Q2, Q3. So they call that Q3, they call that Q1, and this one is Q2. So they want to find the force on this. Okay, so that's the one you are interested in. So that force here is going to be attracted by that one. No, this is positive. You see, that's why you want to use color, right? So it's going to be plus and plus, it's going to be a repel. So they're going to repel each other. Oh, I'm going to make a force maybe in green. Okay, so it's going to be pushed away this way. So that's going to be the force 1, 3. And then those two here, they're going to attract each other. But I am only interested in this one. Okay, so this one will be attracted by that one. And it's going to be along the x-axis here. Okay, it's going to be stronger than this one because the distance is smaller. Okay, so that will be F32. Okay, and they want to find the net force. So the net force will be the vector sum. Okay, so the vector sum will be F net here. Okay, so we have F net is the vector sum of F13 plus F32. So we need to add the component. So let's find the component of 1,3. So F1 on 3. So the x component here is negative. And it's going to be 9 times 10 to the 9. So it's going to be 6, 5. So it's going to be a 5 times 10 to the negative 9 and a 6 times 10 to the negative 9. And here you have the distance between them, 1, 2, 3. So 0.3 squared. And you plug it in, and you should get minus 3 times 10 to the negative 6 Newton. Along the y-axis, there is nothing. Okay, so then you have, I should have F, okay, I'm going to do it here, and between 3 and 2, of 2 and 3, right? So this one has no x component. It has a y component, and it's positive, so positive 9 times 10 to the 9, and then the 5 times 10 to the negative 9, and then I have a 10 to the negative 6. This is 9. This is 10 to the negative 9, and the distance is 0.1 squared, and you get 4.5 times 10 to the negative 6. Okay, so you have F13, exponent is minus 3 micronewton, or 10 to the negative 6 Newton, 0. And then you have another vector here, 1 and 3, 2 and 3. Okay, and the component is 4.5 times 10 to the negative 6. Okay, so you have two vectors. So let's find. Okay, So all you have to do is to add the components. So the net force, so that will be this vector here, has the x component of -3 here, so that will be here. The y component is 4.5 times 10 to the -6 Newton. Talking about that. So we can find the magnitude. So we can factor out the 10 to the -6. And remember, we don't want any minus. So 4.5 squared. And you have a 10 to the -6. So 3 squared plus 4.5 squared, you take the square root. And you get 5.4 times 10 to the -6 Newton. So that will be the magnitude. And then let's say you want that angle here with the negative x-axis. So you have tan alpha. That will be opposite here. Opposite, so it will be the y component. Adjacent will be the x component. And when you do that, you don't, you forget about the negative, right? So tan alpha will be, the y component is 4.5 over adjacent is 3. And then the 10 to the -6 and the 10 to the -6, we don't care because it cross out. So alpha will be 56. Okay? So no, don't put a negative here. So this one is a little bit challenging. It can be very easy, but in that case, they are asking you to find this angle here, which is a little bit challenging, but nevertheless, you need to know how to set up the problem. So anyway, you're gonna have two charges. Maybe they are ping pong balls, for example, very light, and they repel each other. And you have the mass, right? So already the mass we have to convert. Okay, and you have that distance here, 1 meter. Okay, and I'm gonna call that distance d. Okay, which we don't have, but the charge here is 91 times 10 to the -9 coulombs, right? And that here is 1 meter. So the length is 1 meter. So with this kind of problem, the first thing, we're going to use static equilibrium. And we're going to focus here. And the answer, the question is to find the angle. So first of all, it's in equilibrium. So you're going to have a force pushing in this direction. So that will be the electric force, okay? And then you have the tension. So you want the tension to be large enough, T, okay? Because that way the X component will be equals to this, which is not the case here. Yeah. Little bit bigger. Okay. And then you have the force mg. So from physics 1, okay, so this is physics 1. You see that the tension has two components. It has an X component here that will balance out the electric force, and it has a Y component here that will balance out the weight. So I should make the weight a little bit bigger. Okay. So static equilibrium is going to tell us that the Y component here, Ty equals mg, okay? So that will be for the y component. And the x component is balancing out the electric force. And the electric force is K. And we have the charges. And I'm going to write down Q square. Okay, because it's the same charge. And the distance here, if this is D, so that's going to be 2D. So it's going to be 2D squared. Or I can say xq squared over 4d squared. That will be for the x component. Okay? So what's x component? If this is theta, the x component, it's going to be a sine. Here I'm going to have a sine, right? So I'm going to replace the x component by t and a sine. And the y component, it's going to be a t and a cosine. So t cosine. Okay. Okay, that's good. Okay. So that will be equation, I'm going to call that equation 1. I'm going to call that equation 2. And I didn't use yet this 1 meter. Okay, so I want to use it. And I'm going to say equation 3. I see that the sine theta equals opposite, which is d over 1. And then physics stops, right? Because I have all my 3 equations and I have 3 unknown, d, theta, and t. So it's possible to solve, we know that, and it becomes math. So first of all, if you want to eliminate t, okay, you always do the ratio. When you see a sine and a cosine, for example, in that case, it can give you a tangent. But here, I don't want the tangent. I'm just going to take the ratio. So I'm going to take Q1 over Q2, equation 1 over equation 2. So that way, the t is going to go away, right? So I'm going to have sine theta over cosine theta, which is tangent. Sometimes it's useful to turn that into a tangent. And I'm going to divide this by that. So you multiply by the reciprocal times 1 mg. Okay, so it's, okay, I agree. It's a little bit challenging. And what else do you know? I know that equation 3, we have that sine theta equals t. Okay, so, but you will agree with me that this is not physics anymore, right? It's just math. So this, I'm going to plug that into here. I'm going to plug this into here. Okay. So I'm going to get that sine theta over cosine theta equals k q square over 4 sine square theta and S M G. Okay. Okay, so this you can solve because you have only one unknown. So the question is how I'm going to do that. So the easiest way to do it, if it's multiple choices, you have to choose between several angles, right? You have 4.1 degrees and then 8.1 degrees and then I forgot the choices, and you're going to try until you get an equality between them, between those two equations. So I fix it because multiple choices should be 4.1, not just 4, 8.1, not just 8. So you plug into there and you see which one will work. If you want to do it even better, if you want to do it the engineering way, you can say the following. You can say, so that will be the easiest way because you have a test, so you don't want to lose time. But now you can use the small angle approximation. So in that case, you see sine theta is about equals to theta, and theta has to be in radians. And then cosine theta is about equals to 1. You can check on your own. You take a small angle and you see that sine theta equals theta and cosine theta is about equals to 1. So then it will simplify this equation here because you're going to get theta and then equals kq square over 4 theta square mg. So you have the equation here over 4 mg. And if you do that, you find that theta is about 4.1 degrees Celsius. This, it's going to be in radians. Okay, so you have to convert radians into degrees, right? So let's do it quickly. I didn't do it. I did it this way, but this one should work too. So let's see, K, which is 9 times 10 to the negative 9. Okay, so that's good. 91. So multiply by 91 times 10 to the negative. No, that's not good. It's 9 times 10 to the 9. Sorry, so 9 times 10 to the 9 times 91 times 10 to the negative 1 that you square. Okay. You divide by 4. Okay. You divide by the mass 0.005. Okay. You divide by 4 by the mass. Divide by G. Okay. So you get this, but this is radians, right? And you want degrees. So you're going to divide by pi. Can divide by pi to convert into radians. And you multiply by 180. Oh, I forgot to take I will have to cut that. Okay, so let's do this one. So this one, you have to understand what's going on first. So let's see, it's A is, okay. It says that the electric field is going this way. Electric field goes from plus to minus. So that means this plate here is positively charged. It's like 2 electrodes, and this one is negatively charged. So that means that the electron wants to stay here, right? So here it has the lowest potential energy. So if you want the electron to move away from here, it needs some kinetic energy. So that's why it said it's projected. Okay, so that means that the electric force acting on the electron, it's going to be in this direction here, right? So it's very much like gravity. So it's very much like you have the Earth here, and gravity here is going this way, okay, G, and there is a mass, and the mass is very happy here at the ground level. So you need to give it some initial velocity here, right? So it has kinetic energy, and then it's going to go to potential energy, and then it's coming back. So the electron is going to do the same thing. It wants to stay here. So you have to project it. It's going to go to maximum distance here, and it's going to come back. Okay, so it's going to do this. So at that point here, the final velocity equals 0, and then it's coming back. Here it has a potential energy equals 0. And here the potential energy here will be, you see here the potential energy here will be mgh. So potential energy will be q e, and that distance here that I'm going to call delta x that you need to find. Okay, so that will be x. So you have two ways to do it. You can use kinematics, which is also like conservation of energy. Kinematics, if you remember, there was this equation, the final speed square equals initial speed square plus 2 times the acceleration times delta x. But this is actually conservation of energy. So it means the change of kinetic energy equals the work done on the system. Or we can say that the change in kinetic energy equals the change in potential energy. Okay, so if we use this, we need to find the acceleration. So the acceleration is, so the force is in this direction. So the acceleration will be here, right? So acceleration and force, they always have the same direction. So the acceleration will be negative, and then the force will be the electric force divided by the mass. So it will be minus the charge of an electron. So Q, E, the electric field, and the mass, right? You can do the computation and you find minus 2.1 times 10 to the 15 meter per second per second. You can check. The charge of an electron is 1.6 times 10 to the negative 19. Okay, so you have the acceleration. The final speed here is 0. So you have 0 equals the initial speed 10 to the 7th, but it's a square, 10 to the 7th square. Okay, plus 2 times, here we have a minus, and then we have a delta x, and you can solve for delta x, right? Which is 10 to the 14, and then here you have 2, there was a 2 times 2.1 times 10 to the 15. So the answer will be in meters. Okay, so delta x will be 0.025 meters, which is 25 millimeters, right? So that distance here will be 25 millimeters. So that distance here, that's what they want. That distance here will be about 15 millimeters. Okay, so it's close to that. Now, the other way to do it is to say that here the total amount of energy will be its kinetic energy. So it has kinetic energy that will go to potential energy, or we can say that the change in kinetic energy will be equals to the change in potential energy, or the work done by the electric field on the electron. Okay, so change in potential energy, it's the same thing as the work done by the electric field on the electron. So the change in kinetic energy will be final, so it will be 0 minus initial 0.5 mv squared equals, so the work done by the electric field on the electron is negative, so it's going to be minus the work is 4, so QE, times the distance. Okay, so that's the distance delta x. So by the way, this is also the, what you have here is the voltage, right? That's the voltage. Okay, but you can find delta x and you will get the same thing. Okay. So this is actually easy. Just to see if you know the Gauss law. So Gauss law, the electric field, electric flux. It's the number of lines going through a closed surface. Okay. But it also equals to the charge inside the closed surface over epsilon 0. You have a cube here, and it says there is a charge inside, which is positive. So we're going to have an electric field, but the electric field, you see, it's because the distance is not going to be the same. So maybe the electric field here is going to be strong, and here it's going to be weaker. So it's quite complicated. But that's not what they are asking. You see here it's at an angle. They are asking you to find the flux. So all you have to do is to apply that, right? So the flux will be the charge inside is 5 times 10 to the negative 6 over 8.86 times 10 to the negative 12. Okay, and the answer, I think you can do it yourself. So the unit will be a Newton, and then per Coulomb, and then you have a area here. Okay, so let's do this one, and that will be the last one, because the other problems I did it in class. Okay, so you have a uniform linear charge. So this is a linear density, which is lambda. So lambda will be the total charge over the total length. Or we can say it's going to be lambda. So lambda equals dq over dl. Okay? So, but this is lambda, and that is what is given to us. So you see, okay, let's draw first. Okay, let's do it here. So we have the x-axis, and you have 0 here, and then you have a linear distribution of charge between 0, 1, 2, 3. So from here to there. So all that, it's going to be a lot of little charges here. So we can take a little, at that position here, all those little charges, it's going to be dq over a small dx. So here I should put dx and not dl. This is dx. Okay. So here you have a lot of little charge here. Okay. And then they want on the y-axis here. So this is the y-axis. And then they take 1, 2, 3, 4. So 1, 2, 3, 4. So at that point here, we want to know the electric field. So each dq, it's going to generate a small electric field here. So that will be the electric field E, for example, okay, produced by dq. So I'm going to call that dE. D means small e produced by dq. Then my dq here, if I take it here, okay, it's going to also produce a small dE. That's going to be so there, and it's going to be smaller, okay, because it's farther away. And I have even a dq here, and it's going to make a d here. Okay, so you scan every little element dx will carry a dq that will produce a small electric field, and then you need to add them. Okay, so it's a vector, so we add vector, and it's going to be somewhere there maybe, because it's not there. So somewhere here you're going to have a E net. Okay, so I'm going to focus on this one now, produced by that. So I'm going to focus on, maybe I don't see it right here. I'm going to focus on this one, this little GE. Okay. And I'm going to call that distance here. That distance here is going to be the distance X. Okay, so this is X. That is dq. And X will vary between 0 and 3. So this is 3. So you have the dq here, dq, 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 dq. Okay, so let's see, dE in magnitude. Okay, so in magnitude. So here I have 1 coulomb. It's going to be your little, that means small dq. And you have a K, okay? You have your 1 coulomb. And then you have this distance here, but this is 4. So that distance here, I'm going to use Pythagorean theorem. So it's going to be 4 square plus that distance is x square. So it's a square root, but it's going to be square here, right? Because Coulomb's law is here you have a distance square. So you square the distance. Okay, and then they want the y component. So y component, if I call that angle theta, okay, so that angle theta, it's going to be that angle here, right? So it's going to be between here and there. So that's going to be that angle here, theta. That's theta. So the y component of that small dE, it's going to be the magnitude times cosine theta. Okay, so this is the y component here. Okay, so you have dE, you have the y component, and you have the x component, but we focus on the y component. Okay, so n cosine theta equals, I'm going to use that triangle here. It's going to be cosine adjacent over hypotenuse. Okay, so small y component equals the magnitude. So you have a k, and then you have a dq. dq equals lambda dx. So you're going to have k dq, which is lambda dx. Okay, and then you multiply the magnitude. Here we have 4 squared plus x squared. So this is my magnitude, and then I have my cosine. Okay? And I don't know where to write. And then we are done, right? Because this is just math. So dE along the y-axis is going to be k lambda dx. So this is 1 exponent 1, and that's 1/2. So it's going to be 4 squared plus x squared, and that's going to be 3 half. So 1 plus 1.5, and then you have to integrate. So it's going to be integral. So x, that's the variable of integration. So it's going to be between 0 and 3. And here you have 9 times 10 to the negative, not to the 9, sorry. Lambda, which is 2 times 10 to the negative 9. I forgot something. There is a 4. I'm missing a 4. There's a 4. Forgot the 4. There's a 4. There was a 4. Okay. So 4 squared plus x squared to the 3 half. So that goes away. That's gonna be okay, so it's gonna be the integral. 18 times 9 is gonna be 72. And I forgot a dx. Okay. And here I have 4 squared plus x squared 3 half. And then you have to ask Wolfram alpha. How much is that? Okay.